In section 2.2, we introduced the idea of an inverse matrix. And we also learned how to find an inverse matrix. We had an algorithm for doing that. And how to use the inverse matrix to solve a system of linear equations. But that was all very computational. It was actually crunching the numbers. In 2.3, we want to do a deeper dive into the concepts behind invertible matrices. They're somewhat nice for solving systems, but they'll also be really useful as we develop more theory moving forward. They'll give us some powerful tools for a deeper understanding. So I want to take you all the way back to section 1.4. This is where I would insert that little harp music they always use for a flashback. Just go dee-dee-dee-dee-dee-dee-dee. In 1.4 we got Theorem 4, which said these four statements are all equivalent to each other. If one of these statements is true for a matrix, they're all true for that matrix. And likewise, if one of them is false for a particular matrix, they're all false for that particular matrix. So we got this idea that said, hey, if you use this matrix and set up an equation, ax equals b, if that is always solvable for any b, for each and every b in the output, that's one statement. So if that's true, if you can always solve for any b in the range, that means that each b is a linear combination of the columns of A. That's literally what it means to multiply A times X, right? As you're combining the columns of A. And if you can do it for each and every B, that means that the columns of A, when you combine them, they span all of the output space. And that will only happen if you can always solve, which means there has to be a pivot position in every row. So that was Theorem 4, and this was for matrices of any dimension, m by n. Here in Chapter 2, when we're looking at invertible matrices, only square matrices are invertible. So, ta-da! Welcome to Theorem 8, with its many equivalent statements. But they do start us off. They want to point out that we want an n by n matrix. We want a square matrix. As long as that's true, though, then all of these statements live or die together. If one of them is true for a particular square matrix, they're all true for a particular square matrix. Notice we have some familiar statements here. G, the equation ax equals b, has at least one solution for each b. That's the same as the first statement from Theorem 4. So we're kind of starting there, saying if you can always solve, that's the same thing as saying the columns of A span the space. Again, that's the same as C before. And we also have that A has n pivot positions, which is the same as D before. They said pivot position in every row. There were m rows. Now we have n rows, so there are n pivot positions. They don't really restate B here from Theorem 4, that it's a linear combination of the columns of A. We know that's equivalent to these other statements, so they don't resurrect it here. But we do have some new ones, language that we didn't have back in Chapter 1. So for instance, we do know that if the columns span Rn, and you can always solve ax equals b, that means A must be invertible, because that's one way to solve this equation. Let's see, make sure I can write. Yeah, you could take this and if the inverse, that's how you find your solution for each b in Rn. So there's your invertible matrix. See, we already did pivot positions, we already did this one, we already did that one. Let's just take a look at a few of the others. The homework tonight is going to ask you whether various matrices are invertible. And what you don't want to do on the homework tonight is find the inverse of every one. The hope is that you can be more efficient and smarter about it and use one of these other equivalent statements to say, oh, it doesn't have in pivot position, so therefore it's not invertible. And you don't have to do any computations or something else. So keep in mind some of these other statements. Now, if it is square matrix and it's got a pivot in every row, then when you reduce it, it will reduce. There can't be any free variables because it's square, right? So if there's a pivot in every row, that means there's a pivot in every column. And when you fully row reduce echelon form, you'll come all the way down to the identity matrix. It's the same as saying, so if there's a pivot in every row and in every column, then there's not free variables. There's not more than one solution. So another way to say that is AX equals 0 has only one solution, the trivial solution. That's also equivalent to saying that the columns are linearly independent from each other. That's kind of how we found linear independence, was saying AX equals 0 has only the trivial solution. There's no other way to combine the columns and create another one of them. And if there's only one solution set for AX equals 0, there's only one solution set for any other B. That does mean that the solutions are reversible. You can trace them back to where they came from. So it's 1-to-1. And the linear transformation maps the input onto all of the output, which is the same thing as saying span. It's saying, let's see, two more statements. There's a matrix such that C times A is the identity. And what is that matrix? It's the inverse. So A takes care of J and K. Let's see, I think we've gotten all of them except for the last one. We didn't really do a deep dive when we talked about transposes, but there's an easy way to show that if a matrix is invertible, so is the transpose matrix. I'm not going to prove that. The proof is in your book if you're really interested. Okay, so we've got all of these statements, some of which we spend a little more time on than others, but we'll want to be familiar with all of them. So we've got all these statements that are equivalent to each other. So let me take a look at an example or two. So I've got a matrix here that I just made up, but I want to point out that this matrix, the columns, I'm going to start with columns being linearly independent because I think I could just show that to you. 1, 3, 5, 4, 2, 0, those two are not like multiples of each other or anything, so the first two are independent. The big question is, could you somehow combine the first two to make the third one? And just looking at adding them together as is, 1 plus 4 does make 5, 3 plus 2 does make 5, and 5 plus 0 doesn't make 6. So really, if you were going to combine the first two to make the third one, it looks like you'd have to just add them to get the 5 and the 5, but that doesn't give you the 6. So I'm going to claim that these three columns are linearly independent, which means we have a whole bunch of equivalent statements here. The columns, let's see, where's the columns? Linearly independent, that's E. So that means that it should have in pivot positions. It means it's invertible. It means when you row reduce it, it's equivalent to the identity. It means all these other things. So first of all, just calculator check. Is it invertible? Yep, sure is. Get some fractions as it happens. When you reduce it, does it reduce to the identity matrix? Yeah, sure does. And all this means that if this was an A matrix and you had some sort of equation you were trying to solve, and AX equals a B, just making that up. If you were trying to solve an AX equals B, we have two ways of going about it now. One way is, now that we know the inverse, we could just multiply the inverse on each side of this equation. We already kind of know that that cancels. So we could find the solution by doing A inverse times B. Doing this fun little fractional 3 by 3 inverse matrix times 10 negative 3 1. That would give us the solution. And we also know that we could do it by row reducing. We could just augment, instead of reducing this, we could have put 10 negative 3 1 on there and reduced that. I don't know what the 10 negative 3 1 turn into, but I know that there is a solution because there's these 3 pivots here when I reduce this part. Right? The reduction of that part isn't going to change any by slapping a new column on. So you can say, yeah, there's definitely a solution. X1 is going to be this, and X2 is going to be that, and X3 will be that. Okay, so really, invertible, solvable, all the other equivalent statements that we have there. Let's compare that to this one. So I tweaked it just a little bit so that the columns are not linearly independent. Now it is true that if you add the first column plus the second column, you do indeed get the third column. So the columns are linearly dependent, which should mean all the other statements from Theorem 8 are false as well. So if you dump this into your calculator, it'll give you some sort of error message, since this matrix is not invertible. If you reduce, you do not get a pivot in all 3 rows. You only get a pivot in 2 rows, and matter of fact, it tells you exactly how you could combine the first column and the second column to make the third column. It says 1 of the first column, 1 of the second column will make the third column. And we know that we cannot solve for every possible B. Keep in mind, this doesn't mean that it's never solvable for the right B. Of course, you can, with the proper choice of B, it's still solvable. Let's see if I used, 10 negative 3 1 probably is not solvable, but if I pick carefully, let's see. If I pick carefully, well, not that carefully, but something like 1 3 5. Obviously, that's still solvable. If x1 is 1 and x2 and x3 are 0, that's saying take 1 of the first column, 0 of the second and third columns. I can produce 1 3 5. And I can produce anything that's a combination of these 3 columns, which really means just a combination of the first 2 columns. I've still got a plane's worth of solutions. I just don't have all of 3-dimensional space to be solutions. Okay, so that was a quick introduction to the invertible matrix theorem. Believe it or not, we are actually not done building the invertible matrix theorem. We've only got A through L here. That's clearly not enough. As we go on, we're going to find yet more equivalent statements as we get new concepts and new vocabulary to describe those concepts. Okay, in the next video, I'll look at how this actually plays out in the homework. We'll work through a few examples.